Section 5.4 takes us from definite integrals of 5.3 into what's called indefinite integrals. And we also talk about what's called the net change theorem. So let's see what the difference is. We've got an example here where that is a definite integral. And the reason it's called a definite integral is because it has limits of integration here. So this one can be interpreted as finding the area underneath this curve, y equals x squared, between 1 and 2. It's called a definite integral because it's got these limits of integration. And if we evaluate this one, we take the antiderivative of x squared, which using the power rule gives us 1/3 x cubed. And then we use this Leibniz notation, which basically means we're going to evaluate that antiderivative at 2. Then we're going to subtract what we get when we evaluate it at 1. So you get 1/3 times 2 cubed minus 1/3 times 1 cubed. So we get 1/3 times 8, which is 8/3, minus 1/3, so we get 7/3. So when we evaluate a definite integral, the key is we are going to get a number. And how many answers are there? Just one. This question has one answer. And if you integrate correctly, you'll get the same answer that everyone will get. And a definite integral, this one can be done on the TI-83 or 84. Those calculators can handle definite integrals when we have this limit, the lower limit and the upper limit. Okay, now we have an indefinite integral. So we had a definite integral, now we have an indefinite integral. Indefinite integral, you'll notice, doesn't have limits of integration. So when we integrate this, what we're going to get is 1/3 x cubed plus c. We can't evaluate it at the limits of integration because we don't have them. So all we can say is that the answer to this question is a family of functions. There's an infinite number of answers here, but they're all very closely related. They're just this thing plus c. So the thing to take away from this one, when we evaluate an indefinite integral, we don't get a number. What we get is a function plus c. And that's what's going to happen all the time. So indefinite integral, the TI-83 and 84 don't know how to evaluate this because to evaluate this question, you actually need to know what an antiderivative is, right? If you have to have some sort of way of calculating an antiderivative, knowing that we have the power rule here. Where here you don't need to know that. You can use approximation techniques. So the programming is simpler here, which is why the TI-83 and 84 can do this, where to do this question, you need a calculator that has computer algebra software, which is going to typically cost a little bit more. But this is the main takeaway. A definite integral is going to give you a number. It's going to be the answer to a definite integral is a number. The answer to an indefinite integral is a function plus c. And speaking of integrals, here are some rules, and this is a handout that hopefully you have. I typically pass it out in class, but we emailed it to you guys. So these are the rules that you're going to be expected to know when we're in Calc 2. So most of them we've been using all along, right? This is the power rule, and the independent variable here is u instead of x, which may be a little strange looking, but we do this because of this du. So there's this idea of a chain rule built in here. But you won't get into a lot of that until Calc 2. But basically, we know these going backward. We know that the derivative of sine is cosine, so this is just that stated in the reverse order. So the ones that are typically a little trickier are these arc sine, arc tangent, Notice that arc cosine isn't even here because really it's just negative of this. So if you're going to integrate this, you could just have the opposite of this, right? If there's a negative here, you can just do the negative of this instead of memorizing another form here. So there's a hyperbolic ones, which you don't see too much either, but remember the signs of those are different. So we want to be familiar with these because when we get into 5.5, which is use substitution, and that is the last section that we cover as a Calc 1 student, we're gonna have integrands like these, but they won't look like these, but we'll have to transform them into one of these. So we have to be pretty solid on these. So the more you can look at these and try to have them pretty solid, the better life will be. And we will probably add a couple more onto this list once you know use substitution. And then that'll pretty much be it. And then from Calc 2, you'll take it from there and add a few more on. But mainly you'll be learning different approximation or different integration techniques where, again, you'll transform the integral into one of these and also learn approximation techniques. So make sure you spend a decent amount of time looking at these and practicing them. When you do the homework in 5.3 and 5.4 and 5.5, you'll get plenty of practice. Okay, so quick question. See how well you guys were paying attention here. If we've got an indefinite integral like f of x dx, if I evaluate this, what's my answer going to look like? Is it going to be a number? No, it's going to be a function plus c, right? Indefinite integral, I get a function plus c. And basically the function, it's not just any function, it's the antiderivative of that function, right? So the way that our book would do it in 4.9, this would be like capital F of x, right? So the answer to an indefinite integral is going to be a function plus c, and that function will be the antiderivative of that. And the other one, of course, is a definite integral. A definite integral, which looks like f of x dx, but now we have limits of integration a, b, and the answer to this would just be a number, right? That's one that our TI 83 and 84 can do. Okay, so if you're aware of that, that will make life much easier in 5.4 and 5.5 when they mix these up. We just have to know, okay, it's an indefinite integral. I'm not going to get a number answer. I'm going to get a function plus c. Or, oh, it's a definite integral. I'm going to get a number. This can be interpreted as the area underneath this curve between a and b. So I'll get a number answer. So let's try one of these. We'll start off with this is kind of a baby one. This should be pretty straightforward. And we can see we've got radicals here. This is the fourth root of x to the fifth. And if we're going to use a power rule, we're not going to want it written as radicals. We want it written as a rational expression, a rational power. So we just have to remember that the fourth root of x to the fifth is like x to the fifth to the 1/4, which is really x to the 5/4. So we can just rewrite this question. So we have to just kind of notice this is an indefinite integral, which means we're not going to get a number. We're going to get another function, right? A function plus c. So the answer to here, we're going to have to use a power rule. So 5/4 will go up by 1, right? 5/4 plus 4/4 is 9/4. We have to divide by 9/4, which is like multiplying by 4/9. Right? So the power rule says add 1 5/4 plus 1, which is like 5/4 plus 4/4 is 9/4. Instead of dividing by 9/4, we multiply by 4/9, and we get here. And you can always check. If you're not sure, take the derivative of this. If I take the derivative by the power rule, this comes down. 9/4 times 4/9 is just 1x. So I have 1x to the 9/4 minus 4/4, which is 5/4, which is what we got here, which is the same as this. So the integrals in 5.4, they're going to be pretty much like we saw in 5.3. We just won't plug in the endpoints. But they also do have a bunch of homework problems that are definite integrals also. So make sure you practice integration. It's something that you really have to practice. If you just watch me do it, it'll seem okay, like, okay, I think I got it. But you don't. You have to practice it. Everybody who goes through this, everybody who's ever taught calculus, has been through it, there's going to be some stumbling along the way, and you have to get that out of the way in the practice so you can learn the techniques. So make sure you practice those. But other than that, there's really nothing new with them. There's just more integrals, and so, like I said, like I always nag about, homework's super important. But the other thing that they have in this section is the net change theorem. So the net change theorem says this: the integral of a rate of change, what do we call that in calculus? Rate of change, we call a derivative, right? So it says the integral of a rate of change is the net change. The integral of a derivative is the net change. So notice this is the integral of a derivative, f prime of x. Well, this makes sense if you think about it, because what's the antiderivative of f prime of x? F of x. And you know that if you were to integrate this, we would get f of x evaluated. Remember that the vertical line, b up here, a down here. We plug in the b and then subtract the a. So really, all this is the fundamental theorem of calculus. That's all it is. But the net change theorem is like a principle that can be applied to a lot of rate of change problems that you run into in applied settings. So we'll look at some. There's there's actually a lot of good examples of net change. So I'm going to make a little note here. Examples of net change. When you get a chance, take a look at page 406. In the 7th edition, it's page 401. But I think most of you guys have the 8th edition. That's in 406. And it gives a lot of examples of net change from different areas of science and engineering. And the one that we're going to look at in here is physics. So we will look at an example from physics. So here's an example. We've got this object moving along a straight line with position function s of t. And we've seen that a lot of times the position function is s of t, where position is a function of time, t. So if we've got a position function s of t, then its velocity is going to be the derivative of that, right? Velocity is s prime of t. Velocity is the rate of change in position with respect to time. So if we were to integrate velocity, and remember what the net change theorem says, we're integrating a derivative. This is a derivative. So the net change is just going to be the change in position, right? Because the antiderivative of velocity would be position, and then we'd evaluate it at time 2, and then subtract what we get when we evaluate it at time 1. So if we do that, then this difference, s of t2 minus s of t1, is the net change of position or displacement. Right? And the reason I say this is a derivative, because that's just s prime of t. So displacement is something that you'll learn about in physics class. It's a vector quantity. It's like a directed distance. So we'll talk about the distance in here. And we'll talk maybe about directed distance, but just with a plus or a minus, meaning either up, down, or left, right. Also, let's erase this word particle, because we call it object up there. So let's write object right here second. So this difference here, position at time 2 minus the position at time 1 is the net change of position, or the displacement of the object during the time period from time 1 to time 2. But just when you think it couldn't get any better, there's more. Not only is there more, but there's a fancy word we can use too. Okay, here's a word you don't get to use every day. Moreover, right? Who likes that one? Moreover, the acceleration that's 2 C's. Acceleration of the object is acceleration, we've seen that notation before, which is v prime of t. So we've got another integral from time 1 to time 2, and acceleration of t dt is equal to the change in velocity. So velocity at t2 minus velocity at t1 is the change in velocity from time 1 to time 2. All right, so we've kind of done this already. We just didn't formalize it here. Because if you remember before, we were saying that when we started in Calc 1, we would start with the position function. We take the derivative, right, with respect to time to get to the velocity function. And then take the derivative with respect to time to get to the acceleration function. And then we had the problems in 4.9, like the dropped ball problem, where we went from acceleration, we took the antiderivative, then the antiderivative here. So this is really, what we just talked about here is the same thing, right? We have this different notation, but it's saying the same thing. But now we're going to, when you go from acceleration to velocity, like here, we're taking the antiderivative acceleration to get velocity, and then we're going to evaluate at these two endpoints. So that's a little different. Okay, and then we've got a little note here that's going to be important for us. So we'll put this in a different color. We'll go with blue. And the note here is, distance is always positive. I think you already knew that. Right? You never went anywhere and said, wow, that was a long drive, -4 miles. Right, now distance, if you're talking about displacement, then you can put a negative in there, but distance is just a scalar quantity, which you'll see in physics. It's just a number. Directed distance, that's different. That's displacement. But basically, if you want to find the distance, we have to do this. Finding distance is more work than finding displacement. So these are absolute value marks. If we integrate the absolute value of velocity, and we will get the total distance traveled. So when we are told to find the displacement in a problem, which you'll see because we'll do an example, it's an easy question. We just integrate. But when we're told to find the total distance traveled, that's a lot more work, because now we have to deal with this absolute value. And whenever you have absolute values in integration, you have to break this up. We can't integrate the absolute value function. If you remember, it's not differentiable at the peak. So we break it up into, we get rid of this by thinking about whether this is positive or negative on particular intervals, which you'll see. But the point is, finding the total distance traveled is harder than just finding the displacement. Also got another note. I wish I could snap them on the whiteboard in the classroom like this, so they just appear super fast. But another note is this, and this note's going to come in handy when you're dealing with applications in areas that you're not familiar with. So just in general, the unit of measure for something like this, for this integral, this is a definite integral from a to b of f of x dx. And like I said, sometimes some of the questions will be applied problems where maybe it's from chemistry, you're not familiar with chemistry, or it could be from mechanical engineering, could be from anything, could be from the life sciences, but it'll be something that you don't have any intuition for, so you don't just naturally know the units of measure. So an easy way to think of it is it's just going to be the product of the units for f of x and x. And you can see it right here. Whatever this function is going to be units, and dx is a change in x. So if you think of it like this, remember this is like the area, and to get that area we'd think of these infinitely thin rectangles again, you know, where the limit concept comes in. So it's going to be this little change in x, whatever the units of x are, that'll be that dimension. The height dimension is going to be whatever the unit of this function is. So when you integrate this, f of x dx, and you get your answer, you get the number, and then you want to get the units correct, just think it's the unit of the function times the unit of the input of the independent variable. Okay, so that will sometimes help when things are a little tricky. So with this in mind, let's try number 58. So this is on page 410, and it says, if the units for x are feet and units for ax are pounds per foot, so I'm just going to write this down, x, the units for x are feet, the units for a of x are pounds per foot. So it's like pounds per foot, right? Pounds per foot. Then it says, what are the units for dA dx? Well, dA dx, these units would be dA. So this is the change in A, right? A is measured in pounds per foot. So this numerator is going to be pounds per foot. And then the denominator is going to be the unit of x, and x is in feet. So this is going to be in feet. And you typically don't write them like this. Even if it's, if you say it like this, it makes more sense. It's just sort of bulky and awkward. So it's right, like in acceleration, we always have like meters per second squared, even though it doesn't really make as much sense. Meters per second is just too awkward to say. So with something like this, you would almost certainly rewrite it. You would think of this as instead pounds per foot times the reciprocal of the denominator, which would be 1 over foot, which gives us pounds per square foot. Did you ever say, well, how would I abbreviate pound if I were going to start? Now, our English system makes so much sense in every other way. It seems like we'd have a good abbreviation for pound, like, I don't know, P, but no, we have LB. I know I've looked that up before. I think it came from a Latin word for pound or something like that. But anyway, we just normal stuff with our system. Nothing really seems to make sense. But anyway, this is how you would find dA dx. And then it says, what about these units? So the other question is, we've got this integral from 2 to 8, which means it's a definite integral, ax dx. So the units of this would be the unit of A, whatever that is, which is pounds per foot, times the unit of dx, which is the unit of x, right? It's the change in x. X is in feet. So that would cancel, and we just get the unit of pounds. Then we should look at one more problem. Let me see how fast I can type this one up. How's that for fast typing? Okay, so find the displacement. That's the easy one. Displacement is just the change in position. And finding the displacement is easy because we just have to integrate. So just to think of, just so we're clear on what this means. Let's say somebody is walking from right here. We're going to start right here. This person walks here, and then they stopped and they come back here, right? And then they go back over here. Well, if you say what's the displacement, the displacement is just this, it's actually a vector, but we're basically finding this distance. Here's a displacement, is this distance with a direction, but here it is. But that's definitely not the distance they traveled, right? Because they started here, went to here, came back to here, and then went to here. So the distance is definitely further than this, right? So displacement is just, we're going to find the magnitude of the difference between where they started and where they stopped. And then we'll find you see there's a direction associated too. But it's easier to find the displacement. If you're asked to find the displacement, we just have to integrate. We don't really have to think about it. We're basically just looking at this distance here with a direction. Meaning if they want, the displacement is going this way to the right or to the left or up or down. Where distance won't have a direction, but distance is harder because we have to think, well, first they went here, how far was that? Then they went here, you know, what distance was that? And then they went back here, we have to add all those distances in. But displacement, easy, it's just the net change of position. Displacement is the net change in position, and it's a much easier one to find. So let's find this displacement first, then we'll talk about the distance. So to find the displacement, we just have to integrate the velocity. We're using the net change theorem right here. Because velocity is a derivative, we're going to integrate this derivative, and we're going to get the change in the original function. So we're going to get the change in position. So looking at this is a definite integral. This is like we learned in 5.3. We find the antiderivative of this, and then plug in these endpoints. So we will get, using the power rule, 1/3 t cubed minus t squared, right? T squared because this t goes up by 1 to 2. Then we divide by 2, so the 2's cancel. And then we get minus 8t from 6 to 1. So remember, if this is a test or a quiz, I need one more step here, right? I need one more step. This is what we need. Show me that you know that the 6 goes here, and that the 1 comes next after you put a minus in there, right? So plug in the 1, we're just going to get this. Now after this, you can just put your answer. You don't have to do any work here, right? I know everybody's capable of doing arithmetic, so you can put your answer right here. So if we, I guess we can, I'll just go one more step here. So we get 6 cubed is 216, divided by 3 gives us 72, minus 36, minus 48, minus 1/3 plus 1 plus 8, right, because I distribute the negative through. And if you go through and clean that up, you get negative 10/3 meters. So we want to have the units on here, negative 10/3 meters. The significance of the negative just means we're like, if we think of our starting point as the origin, if we think of going to the right as being positive, that means we're to the left of the origin. So we went to the negative direction, and the unit, or the amount of change we had in position, was 10/3 meters. Okay, so we could also check, just to verify that it's going to be in meters. This is velocity, right? Meters per second, because it told us velocity was measured in meters per second. And then time would be seconds, right? So the change in time would be seconds. So if you multiply those, you get meters, which is what we got, negative 10/3 meters. And then the other question they're going to say is find the distance traveled during the given time interval. Okay, so now we want to find the distance traveled during the given time interval. I found out it's actually faster just write by hand than it is to type. But we want to see the difference here between the displacement and the distance traveled. And displacement's much easier. Distance traveled is going to be a little bit of work because we have to remember something about distance traveled. we have to remember that the distance is equal to the integral of the absolute value of the velocity. These are straight lines here. And whenever you have to integrate absolute value, we're going to have to break this up into pieces. We need to break this up into pieces to get it out of here, to get it out of the absolute value. And we're going to just use the formula we've seen before. We're going to think of it like, well, here's absolute value of x is equal to x if x is greater than or equal to 0. It's equal to negative x if x is less than 0. So we're going to use that same thing, and that allows us to, if you notice here we've got absolute value, here we don't. And so before we integrate it, we're going to break it up into pieces so that we can get rid of the absolute value. So we just have to think about where velocity is positive and where velocity is negative. So in order to do that, let's take a look at velocity. So it told us that velocity is this. It's t squared minus 2t minus 8. And we're interested in this time between 1 and 6 seconds. We basically need to figure out when is velocity positive and when is it negative. So it's sort of like, you might remember these kind of questions you had in algebra. It says solve this inequality, right? We want to figure out when is this positive, when is it negative. And a lot of times what you do is you first just figure out, well, when is it 0, right? You figure out when is it 0, and I can break up this the number line and find some test points to plug in to see when the velocity is positive and negative. And we've done things similar to that. So let's figure that out first. We got velocity. Let's figure out where is velocity equal to 0. So if we factor this one, 2 times 4 minus and plus, so we would get t equals negative 2 and t equals 4. Now one of these we can eliminate right away, right? Time is not going to be negative, so even though negative 2 is a solution to this, it doesn't work for our situation where time is between 1 and 6. So basically, we've got this number line between 1 and 6. So we've got this number line here between 1 and 6. That's what we're interested in. And we know that at 4, velocity is 0. So we basically know if the velocity is positive at 2, it's positive at 3, right? The only time it could change to negative is by hitting 0 first and then changing. So we need a test point on this interval and this interval. So I'll just pick 2 and 5 and just plug them in to velocity with a test point. You could plug it right in, right in here if you want, but it's easier just to plug it in here. If I plug a 2 in here, I'm going to get 4, which is positive, times negative 2, which is negative. So I'm going to get negative. So velocity is negative here. So on this interval, velocity is negative. Velocity is negative here. And then if you plug in a 5 here, you're going to get a positive times a positive, so it's positive over here. Okay, so here's what we're going to have to do. We're going to have to think of this displacement, but we're going to have to break it up at 4. So what we have to do is this. We're going to find the distance. Let me write this whole thing out so we can get a good idea of what we have to do. So now the distance is equal to the absolute value of the velocity, right? So this absolute value, this weird kind of function in here, and we can't do it. Whenever you have something like this, an integral with absolute value, and you'll see them next semester too, we have to get rid of the absolute value. So we know that this thing is going to be negative from 1 to 4. So what we're going to do is we're going to treat it just like when we had the absolute value of x, right? So, okay, I'm going to write something underneath here, then I'll erase it. But I guess the advantage of this is you can always look back. So let me do something here to show, like when we had absolute value of x, this is what we did. We said, oh, it's x if that input is positive, and it's negative x if that input x is negative. Let's do the same thing here. I'm going to model this piecewise defined function on this one, and we can always model these on this one. So this is equal to the positive version of itself if that thing is positive, right? If t squared minus 2t minus 8 is greater than or equal to 0. And we know it happens whenever the velocity is positive when t is between 4 and 6 in our case, right? We're only interested in this little window from 1 to 6. So we know that this absolute value is equal to this if this is greater than or equal to 0. And where is this thing greater than or equal to 0? Between 4 and 6. Right? And then we also know that this absolute value is equal to the opposite of this if this thing right here is less than 0. We know this thing is less than 0 on this interval here where the velocity is negative from 1 to 4. So when we integrate this thing, we have to break it up into two pieces. We can't have the absolute value, so I guess I'll just leave it like this. I'll do something like this. So we can see these, we can see this stuff here. So this is going to be equal to, well, we're going to go, let's see, it's negative from 1 to 4. So we're going to break this interval from 1 to 6 into two parts. We're going to go 1 to 4 and then 4 to 6, right? 1 to 4 and then 4 to 6. And from 1 to 4, the absolute value of t squared minus 2t minus 8 is actually negative t squared minus 2t minus 8 dt, right? From 1 to 4, this absolute value is exactly the same as this thing, right? It's the same as this thing where this is less than 0. Where is this less than 0? It's negative from 1 to 4. And then we add to that, we need the rest of the interval. So we have 1 to 4, so now we go 4 to 6. And here it's positive, so the absolute value of t squared minus 2t minus 8 is the same as t squared minus 2t minus 8. So see, when they ask you to find the distance, it's more work. We're going to have to break these things up to get rid of the absolute value, because we're never going to integrate absolute value. We're always going to break that up. So then we can go ahead and integrate. So we're going to get, let's see, let me do one more step here and just distribute this through minus t squared plus 2t plus 8 dt plus 4 to 6 t squared minus 2t minus 8 dt. So this would be negative 1/3 t cubed plus t squared plus 8t from 4 to 1 plus 1/3 t squared minus t squared minus 8t from 6 to 4. Okay, so if this is a test question, I need one more step, one more, because I need to be convinced that you're not going to reverse these, and students reverse them all the time. So if you do one more step, then I'll know that you know exactly how to do the calculus. So I plug in a 4, so I get negative 1/3 times 4 cubed plus 4 squared plus 8 times 4 minus, now I plug in the 1, minus 1/3 plus 1 plus 8, right? So this whole thing here is this first part. Then we go plus. So I have plus. Plug in the 6 here, so you get 1/3 6 squared minus 6 squared minus 8 times 6 minus, now I plug in the 4, 1/3 4 squared minus 4. Oh man, this is a cubed here. Sorry guys, it's a cubed. Surprised I didn't hear you yelling at the screen. We're coming right out of the screen. So that's going to be 1/3 6 cubed See, I need you guys to be out there in the classroom so you can correct me when I do these old guy mistakes. So this is going to be 1/3 4 cubed minus 4 squared minus 8 times 4. Okay, that from that point you could just tell me the answer. Because this from here is just a whole lot of arithmetic, and normally when you're all done, you should get 98/3 meters. And that distance will always be a positive number. If you do everything right, distance will always be positive. A displacement could be positive or negative. So go ahead and give 5.4 a try. It's a lot like 5.3, honestly, but now we know the difference between a definite integral and an indefinite integral. So give them a try and let me know if you have any questions.